Hello, I'm Aryan, and today we'll be discussing the Fourier transform. In theory, a Fourier transform is a mathematical operation that breaks down a complex wave-like signal into its individual simpler sine and cosine functions. We can think of it like a prism separating white light into a rainbow and seven different colors. The formula for the Fourier transform is the multiplication of the time function with an exponential function, and you take the integration of the function with respect to time. We'll come back to the formula, but first let's take an example. So I decide to play a piano, and let's say I play the C key first, which has an amplitude of 220 hertz. If I had to plot that out, its graph will look something like this. And then after that, I decide to play the B key, which has an amplitude of maybe 260 hertz. Its graph will look something like this, a little bit tighter. And then I play the F key, which has an amplitude of, let's say, 350 hertz. So its graph will look something like this. You see how the graph is traveling a little bit faster. So the wave is not traveling like if when we talk about the speed, the wave is not traveling faster. All the waves are traveling at the same time, at the same speed. But it's just that the amplitude, the oscillations of the amplitude of the wave, which has 360 hertz, just makes more oscillations. And if I had to add all of these three functions, its graph would look something like this. No, like this, and come down, something like this, something. All right, it will look like this. And let's say when you're recording yourself playing a piano, it's not just the sound of the piano. There might be some random background noises, or maybe you hear a sudden screech from outside the window. So the recorder would capture all of this. So it's important, it would be important to filter all of this sound so that you can get the clean, undistorted sound of the piano. And first of all, before going to random noises, we'll first see how we added all of these functions. So I take two random functions, for example, sine 3x and sine x. And if I had to plot both of these functions, the sine x function will look something like this. It approaches 1, and then it approaches -1 at 2 pi. And the sine 3x function, it approaches 1 at pi by 4, I guess. And then it approaches -1 and right here. So this is how the graph of the sine 3x function will look like. So if I take one point from the graph, for example, if I take this one, where the two waves coincide at 3 pi by 4, so the value of sine x at 3 pi by 4 would be 1 upon root 2. And the value of the function sine 3x at 3 pi by 4 would be 1 upon root 2 as well. So the addition of those two would be 1 upon root 2 plus 1 upon root 2, which would be root 2. And this is the addition. But if I take a point, if I take both of the functions at pi by 2, and this one at pi by 2, this will be like this. So we can see that sine x at pi by 2 is 1, as opposed to sine 3x, which is 0. So if we were to take the addition of both of the functions, they would just cancel out each other, and there would be no resulting wave from that. And if I just keep on adding functions like this and plotting and keep on plotting them out, its graph will look something, it will look like this. So this is the graph, and then I keep adding more sine 3x, sine 1 by 2 to 4x. I just keep on adding more functions. So the residual graph or the resulting graph of all of the addition will look something like this. And the way we plotted the graph, so let me show you how I plotted the graph. So this would be like this, and look at this. So uh, when both of the values were zero, and it will be at zero, like this, like this, like this. So when both of the values were zero, when the function was zero, and then when the value was at 3 pi by 4, the function was right here. So you can see that as we keep adding on functions, the wave will more resemble a square wave. So the function just keeps getting closer to the square waves as we keep on adding more functions. And why do we do that? Why would we keep on adding functions? It's because, let's say, if I wanted to find the difference between two waves, for example, I take the first wave as, let me say, let me take the sawtooth wave. This is the sawtooth wave. And let me take the square wave like this. The square wave will look something like this. Okay, this is the square wave. So let's say that the function of the sawtooth wave is something like sine x minus 1 by 2 sine x, 2x plus 1 by 3 sine 3x. And the function for the square wave might be sine x plus 0 sine 2x plus 1 by 3 sine 3x. We're just taking random functions. So how will we know what wave does that function result into? And we know we can find it by just seeing the amplitude of the function. So for example, if there's a function sine x plus 1 by 2 sine x, so we can just take the amplitude of the function and we can see what pattern or what kind of wave that it is creating. And we apply the transformation in order to get a Fourier series. So the original function, it tells us how the function changes with time. And then the Fourier series, it tells us the sum of the different frequencies or how the graph will look like when we add the frequencies of the different functions. And the applications of the Fourier transform are diverse. We can use it in pattern and shape recognition. We can use it to analyze image. What are the constitutes of an image? And then we can use it to recognize the shapes as well, all the different shapes we've got in the image. And in computer vision, we might use to maybe segment the image or maybe find shapes in an image. For example, if you're trying to disseminate an apple from a pizza, we can use the Fourier transform just to differentiate the two shapes between them. So coming back to the original example that I took first. So we added all the three functions, we got this wave, and if we pass it through a Fourier transform, so we got a Fourier series which looked something like this. This was the Fourier series which resembled a square wave. All right, then it resembled a square wave, something like this. And then if we pass it through a Fourier transform, the result would look something like this. So we get the frequency of different amplitude. So this wave, this frequency would have this much amplitude. This frequency would say, it would have 180 hertz amplitude. And this frequency would have 400 hertz of amplitude. And this frequency would have 190, let's say. So it just gives us the different frequencies and what their amplitude it is and the frequency. And if we come back to the original example where we added the three keys, the sound from the three keys, and we say that you can capture some background noises, and maybe let's say there's a loud screech coming from outside the window. And if we were to plot that, it would be something like this. So let's say these are the keys that you play from the piano. This is the C key, which had the amplitude of 320 hertz. This was the D key, which had the amplitude of 190 hertz. This was the F key, which had an amplitude of 320 hertz. So this is the frequency of the amplitude of the keys that you're playing. And together with that, let's say you captured some background noise as well. So this was all the background noise, maybe some people talking or any kind of small perturbations in the background. And let's say you hear a loud screech, which is captured by the recorder, which would have a different frequency than all the other sounds. So how you use the Fourier series is that you can separate all these sounds into their different frequencies, and you can just you can just remove them from they go this one, and then you can remove this one as well. So you can just remove all the unwanted sounds and keep all the important sounds from the piano. For example, how we capture the sounds from the piano. So this can be used in noise cancellation. So what we explained right here was noise cancellation. You record a sound and then you try and filter out all the unwanted noises. So that is essentially how a Fourier transform works. And so you can see right here. The formula was the time function plus an exponential function. So this exponential function is nothing but the Euler's theorem, which tells us right here down. So it says that the exponential function is nothing but just an amalgamation, a mixture of the cos and sine waves. So that's why we get the formula for Fourier transform as the time function multiplied by the exponential functions, which is nothing but just the cos and sine waves of that function. We integrate it with respect to time. So that's why we say the Fourier transform is nothing but just a mixture of the cos and sine signals.